So today we're going to be reading some Roussel, philosopher guy. Roussel, The Natural Numbers, Piano and Frege. Mathematics is a study which, when we start from its most familiar portions, may be pursued in either of two opposite directions. The more familiar direction is constructive, towards gradually increasing complexity, from integers to fractions, real numbers, complex numbers, from addition and multiplication to differentiation and integration, and on to higher mathematics. The other direction, which is less familiar, proceeds by analyzing to greater and greater abstractness and logical simplicity. Instead of asking what can be defined and deduced from what is assumed to begin with, we ask instead what more general ideas and principles can be found, in terms of which what was our starting point can be defined or deduced. It is the fact of pursuing this opposite direction that characterizes mathematical philosophy as opposed to ordinary mathematics. But it should be understood that the distinction is one, not in the subject matter, but in the state of mind of the investigator. Early Greek geometers, passing from the empirical rules of Egyptian land surveying to the general propositions by which those rules were found to be justifiable, and thence to Euclid's axioms and postulates, were engaged in mathematical philosophy. According to the above definition, but when once the axioms and postulates have been reached, their deductive employment as we find it in Euclid belong to mathematics in the ordinary sense. The distinction between mathematics and mathematical philosophy is one which depends upon the interest inspiring the research, and upon the stage which the research has reached, not upon the propositions with which the research is concerned. We may state the same distinction in another way. The most obvious and easy things in mathematics are not those that come logically at the beginning. They are things that, from the point of view of logical deduction, come somewhere in the middle. Just as the easiest buys to see are those that are neither near nor very far, neither very small nor very great, so the easiest conceptions to grasp are those that are neither very complex nor very simple, using simple in a logical sense. And as we need two sorts of instruments, the telescope and the microscope, for the enlargement of our logical powers, one to take us forward to the higher mathematics, the other to take us backward to the logical foundation of the things that we are inclined to take for granted in mathematics, we shall find that by analyzing our ordinary mathematical notions, we acquire fresh insight, new powers, and the means of reaching whole new mathematical subjects by adopting fresh lines of advance after our backward journey. It is the purpose of this work to explain mathematical philosophy simply and untechnically, without enlarging upon those portions which are so doubtful or difficult that an elementary treatment is scarcely possible. A full treatment will be found in Principia Mathematica. The treatment here is intended merely as an introduction. To the average educated person of the present day, the obvious starting point of mathematics would be the series of whole numbers, 1, 2, 3, 4, etc. Probably only a person with some mathematical knowledge would think of beginning with 0 instead of with 1. But we will presume this degree of knowledge. We will take as our starting point the series 0, 1, 2, 3, n, and n plus 1. And it is this series that we shall mean when we speak of the series of natural numbers. It is only at a high stage of civilization that we could take the series as our starting point. It must have required many ages to discover that a brace of pheasants in a couple of days were both instances of the number 2. The degree of abstraction involved is far from easy. After the discovery that 1 is a number must have been difficult. As for 0, it is a very recent addition. The Greeks and Romans had no such digit. If we had been embarking upon mathematical philosophy in earlier days, we should have had to start with something less abstract than the series of natural numbers, which we should reach as a stage on our backward journey. When the logical foundations of mathematics have grown more familiar, we shall be able to start further back, at what is now a late stage in our analysis. But for the moment, the natural numbers seem to represent what is easiest and most familiar in mathematics. But though familiar, they are not understood. Very few people are prepared with a definition of what is meant by number or 0 or 1. It is not very difficult to see that starting from 0, any other of the natural numbers can be reached by repeated additions of 1, but we shall have to define what we mean by adding 1 and what we mean by repeated. These questions are by no means easy. It was believed until recently that some, at least, of these first notions of arithmetic must be accepted as too simple and primitive to be defined, since all terms that are defined by means of other terms. It is clear that human knowledge must always be content to accept some terms as intelligible without definition in order to have a starting point for its definitions. It is not clear that there must be terms which are incapable of definition. It is possible that, however far back we go in defining, we always might go further still. On the other hand, it is also possible that, when analysis has been pushed far enough, we can reach terms that really are simple, and therefore logically incapable of the sort of definition that consists in analyzing. This is a question which is not necessary for us to decide. For our purposes, it is sufficient to observe that, since human powers are finite, the definitions known to us must always begin somewhere, with terms undefined for the moment, though perhaps not permanently. All traditional pure mathematics, including analytical geometry, may be regarded as consisting wholly of propositions about the natural numbers. That is to say, the terms which can be defined by means of the natural numbers, and the propositions can be deduced from the properties of natural numbers, with the addition in each case of the ideas and propositions of pure logic. That all traditional pure mathematics can be derived from natural numbers is a fairly recent discovery, though it had long been suspected. Pythagoras, who believed that not only mathematics but everything else could be deduced from numbers, was the discoverer of the most serious obstacle in the way of what is called the arithmetizing of mathematics. It was Pythagoras who discovered the existence of incommensurables, and in particular, the incommensurability of the side of a square in a diagonal. If the length of the side is 1 inch, the number of inches in the diagonal is a square root of 2, which appeared not to be a number at all. The problem thus raised was solved only in our own day, and was only solved completely by the help of reduction of arithmetic to logic. Having reduced all traditional pure mathematics to the theory of the natural numbers, the next step in logical analysis was to reduce the theory itself to the smallest set of premises and undefined terms from which it could be derived. This work was accompanied by Peano. He showed that the entire theory of the natural numbers could be derived from 3 primitive ideas and 5 primitive propositions in addition to those of pure logic. These 3 ideas and 5 propositions thus became, as it were, hostages for the whole of traditional pure mathematics. If they could be defined and proved in terms of others, so could all pure mathematics. Their logical weight, if one may use such an expression, is equal to that of the whole series of sciences that have been deduced from the theory of the natural numbers. The truth of this whole series is assured if the truth of the 5 primitive propositions is guaranteed, provided, of course, that there is nothing erroneous in the purely logical apparatus which is also involved. The work of analyzing mathematics is extraordinarily facilitated by this work of Peano's. The 3 primitive ideas in Peano's arithmetic are 0, number, successor. By successor, he means the next number in the natural order. That is to say, the successor of 0 is 1, the successor of 1 is 2, and so on. By number, he means, in this connection, the class of natural numbers. He is not assuming that we all know the members of the class, but only that we know what we mean when we say that this or that is a number, just as we know what we mean when we say Jones is a man, though we do not know all men individually. The 5 primitive propositions which Peano assumes are: 0 is a number, the successor of any number is a number, no 2 numbers have the same successor, 0 is not the successor of any number, any property which belongs to 0, and also to the successors of every number which has the property belongs to all numbers. The last of these is the principle of mathematical induction. We shall have much to say concerning mathematical induction in the sequel. For the present, we are concerned with it only as it occurs in Peano's analysis of arithmetic. Let us consider briefly the kind of way in which the theory of the natural numbers results from these three ideas and 5 propositions. To begin with, we define 1 as the successor of 0, 2 as the successor of 1, and so on. We can obviously go on as long as we like with these definitions, since in virtue of 2, every number that we reach will have a successor, and in virtue of 3, this cannot be any of the numbers already defined, because if it were, two different numbers would have had the same successor, and in virtue of 4, none of the numbers we reach in a series of successors can be 0. Thus, the series of successors gives us an endless series of continually new numbers. In virtue of 5, all numbers come in this series, which begins with 0 and travels on to successive numbers. For A, 0 belongs to the series, and B, if a number n belongs to it, so does its successor. Once by mathematical induction, every number belongs to the series. Suppose we wish to define the sum of two numbers. Taking any number m, we define m plus 0 as m, and m plus n plus 1 as the successor of m plus n. In virtue of 5, this gives a definition of the sum of m and n. Whatever number n may be, similarly we can define the product of any two numbers. The reader can easily convince himself that any ordinary elementary proposition of arithmetic can be proved by means of our 5 premises, and if he has any difficulty, he can find the proof in Peano. It is time now to turn on to the considerations which makes it necessary to advance beyond the standpoint of Peano, who represents the last perfection of the arithmetization of mathematics, to that of Frege, who first succeeded in logicizing mathematics, i.e., in reducing to logic the arithmetical notions which his predecessors had shown to be sufficient for mathematics. We shall not, in this chapter, actually give Frege's definition of number and of particular numbers, but we shall give some of the reasons why Peano's treatment is less final than it appears to be. In the first place, Peano's 3 primitive ideas, namely 0, number, and successor, are capable of an infinite number of different interpretations, all of which will satisfy the 5 primitive prepositions. We will give some examples. 1. Let 0 be taken to mean 100, and let number be taken to mean the numbers from 100 onward in the series of natural numbers. Then all our primitive prepositions are satisfied, even the 4th, for through 100 is the successor of 99. 99 is not a number in the sense which we are now giving to the word number. It is obvious that any number may be substituted for 100 in this example. 2. Let 0 have its usual meaning, but let number mean what we usually call even numbers, and let the successor of a number be what results from adding 2 to it. Then 1 will stand for number 2, 2 will stand for number 4, and so on. The series of numbers now will be 0, 2, 4, 6, 8. All Peano's 5 premises are satisfied. Still, let 0 be the number 1. Let number mean the set 1, 1/2, 1/4, 1/8, 1/16. And let successor mean half. Then all Peano's 5 axioms will be true of this set. It is clear that such examples might be multiplied indefinitely. In fact, given any series, x0, x1, x2, x3, and xn, which is endless, contains no repetitions, has a beginning, and has no terms that cannot be reached from the beginning in a finite number of steps. We have a set of terms verifying Peano's axioms. This is easily seen that the formal proof is somewhat long. Let 0 mean x0, let number mean the whole set of forms, and let the successor of xn mean xn plus 1. Then, 1, 0 is a number, i.e. x0 is a member of the set. 2, the successor of any number is a number, i.e. taking any term xn in the set, xn plus 1 is also in the set. 3, no 2 numbers have the same successor, i.e. if xm and xn are 2 different members of the set, xn plus 1 and xn plus 1 are different. This results from the fact that, by hypothesis, there are no repetitions in the set. 4, 0 is not the successor of any number, i.e. no term of the set comes before x0. 5, this becomes any property which belongs to x0 and belongs to xn plus 1, provided it belongs to xn, belongs to all the x's. This follows from the corresponding property for numbers, a series of the form x0, x1, x2, x3, xn, etc., in which there is a first term, a successor to each term, so that there is no last term, no repetitions, and every term can be reached from the start in a finite number of steps, is called a progression. Progressions are of great importance in the principles of mathematics. As we have just seen, every progression verifies Peano's 5 axioms. It can be proved, conversely, that every series which verifies Peano's 5 axioms is a progression. Hence, these 5 axioms may be used to define the class of progressions. Progressions are those series which verify these 5 axioms. Any progression may be taken as the basis of pure mathematics. We may give the name 0 to its first term, the name number to the whole set of its terms, and the name successor to the next in the progression. The progression need not be composed of numbers. It may be composed of points in space, or moments of time, or any other term of which there is an infinite supply. Each different progression will give rise to a different interpretation of all the propositions of traditional pure mathematics. All these possible interpretations will be equally true. In Peano's system, there is nothing to enable us to distinguish between these different interpretations of his primitive ideas. It is assumed that we know what is meant by 0, and that we shall not suppose that this symbol mean 100, or Cleopatra's Needle, or any of the other things that it might mean. This point, that 0 and number and successor cannot be defined by means of Peano's 5 axioms, but must be independently understood, is important. We want our numbers not merely to verify mathematical formulae, but to apply in the right way to common objects. We want to have 10 fingers and 2 eyes and 1 nose. A system which 1 meant 100 and 2 meant 101, and so on, might be all right for pure mathematics, but would not suit daily life. We want the 0 and numbered successor to have meanings which will give us the right allowance of fingers and eyes and noses. We have already some knowledge, though not sufficiently articulate or analytic, of what we mean by 1 and 2, and so on, and our use of numbers in arithmetic must conform to this knowledge. We cannot secure that this shall be the case by Peano's method. All that we can do, if we adopt his method, is to say we know what we mean by 0 and number and successor, though we cannot explain what we mean in terms of other simpler concepts. It is quite legitimate to say this when we must, and at some point we all must. But it is the object of mathematical philosophy to put off saying it as long as possible. By the logical theory of arithmetic, we are able to put it off for a very long time. It might be suggested that instead of setting up 0 and number and successor as terms of which we know the meaning, although we cannot define them, we might let them stand for any 3 terms that verify Peano's 5 axioms. They will then no longer be terms which have a meaning that is definite though undefined. They will be variables, terms concerning which we make certain hypotheses, namely those stated in the 5 axioms, but which are otherwise undetermined. If we adopt this plan, our theorems will not be proved concerning as an uncertain set of terms called the natural numbers, but concerning all sets of terms having certain properties. Such a procedure is not fallacious. Indeed, for certain purposes, it represents a valuable generalization, but from 2 points of view, it fails to give an adequate basis for arithmetic. In the first place, it does not enable us to know whether there are any sets of terms verifying Peano's axioms. It does not give the faintest suggestion of any way of discovering whether there are such sets. In the second place, as already observed, we want our numbers to be such as can be used for counting common objects, and this requires that our numbers should have a definite meaning, not merely that they should have certain formal properties. This definite meaning is defined by the logical